Good day, all. I am Ed Twiss.
And I am John Haber.
We are with Analytical and Combustion Systems, here to present on boiler and generator fuel oil pumping and distribution.
We will be having a live question and answer session at the end of the webinar. However, if you have any quick questions, you can use the chat box during the webinar. Otherwise, please feel free to email us directly. Off to you, Ed.
Thank you, John. The goal of this presentation is to provide an overview of fuel oil handling systems. We will discuss basic topics and applications, including fuel oil system layout, fuel oil pumping basics, pump types and characteristics, fuel oil systems applications for emergency generators and boilers and burners, pump set selection, fuel oil system design, and something becoming more and more critical, the long-term storage of fuel oil, especially with low sulfur, ultra-low sulfur, and biofuels.
And a couple points here is on strategy. I mean, there's a large range that we can discuss at future times. And also when we talk about low sulfur fuels and ultra low sulfur and bio, I mean, there's a lot of water in those molecules, Ed, right? So
Yes.
really you have to pay close attention to how much storage you have in the facility, and the realization that you really do want to filter.
You need to filter and polish.
Water it.
You need to filter and polish and dewater it because those old high sulfur fuels had antibiotics in them. The new low sulfur fuels do not. This slide pictures most of the equipment that you might find in a fuel oil system and is a good roadmap. Here we can see underground tanks, above ground tanks, and their ancillary equipment. Some specialties you may not find in chilled or hot water systems, such as item 10, an anti-siphon valve, item number 9, a tank selector valve, and item 27, a fire safety lever gate valve, which will be discussed in more detail later. Probably the most critical aspect of a fuel oil system is getting the oil to the pump. Unlike chilled or hot water systems, which are pressurized by expansion tanks, fuel oil systems typically operate in a vacuum on the suction side of the pump. For this reason, NPSH is critical. NPSH-A, net positive suction head available, is a function of the system. You, as designers, have influence on this based on elevation changes, pipe routing, and sizing and number of fittings. NPSH-R, the net positive suction head required, is a function of the pump. This is the pressure required at the inlet of the pump to prevent the pump from cavitating. When the NPSH-A is less than the NPSH-R, we have cavitation. Cavitation occurs when the liquid is reduced to the vapor pressure of the fluid at the actual temperature. This reduces efficiency and damages the pump. For this reason, your NPSH-A must always be greater than the NPSH-R to prevent cavitation.
Ed, have you ever heard a pump cavitate?
Yeah, it sounds like we're grinding up a bunch of marbles in that pump, and you hear it from all the way down the hallway. Doesn't sound very good.
Yeah, I think it tends to have people want to head for the door.
Especially in a high-end hotel. Not very good.
Well,
This slide is a great representation of a demonstration of cavitation occurring in a rotary gear pump, which is typically used in a fuel oil system. Those little vortexes there are your fluid flashing.
It's quite unique to be able to just see that discoloration with the swirl at the exit of the gears after they mesh.
And it's pretty hard to believe that those little vortexes can actually eat away metal, huh?
Just imagine they're running for 10 hours like this.
Oh, yeah. To prevent cavitation, we must stay above the vapor pressure line. In a fuel oil system operating in a vacuum condition on the suction side of a pump, we end up with an elevated vapor pressure line, which facilitates cavitation in an improperly designed system. Why positive displacement pumps? Positive displacement pumps are the pump of choice of fuel oil. They are able to pump viscous liquids. They provide lift, constant flow over a wide range of operating pressures, and are self-priming to a point. The pump flow is determined by motor RPM, and pump pressure is determined by the motor horsepower. Also, positive displacement pumps are required by code for fuel oil transfer pumps.
And the other thing about positive displacement pumps is actually per code in New York City and actually the international code.
Correct.
For fuel burning devices, you have to have positive displacement pumps.
That is correct, John. This slide is a comparison of positive displacement pumps and centrifugal pumps. The performance graph shows the capacity versus head. As you can see, the positive displacement pump has a constant flow rate over a wide range of operating pressures. The centrifugal pump flow rate reduces as the head increases. The efficiency of a positive displacement pump is constant also over a wide range of operating conditions. For a centrifugal pump, you must design for the best efficiency point, which is the peak of the curve. Viscosity up to a point increases the flow rate of a positive displacement pump. For instance, the flow rate for number 6 oil is higher than the flow rate for number 2 oil. Centrifugal pumps will not pump viscous fluids. Examples of positive displacement pump curves. When you ask us for curves, you'll get a bunch of straight lines. As you can see, the speed of the pump determines the flow rate. The higher the RPM, the higher the flow rate. And as you can see, the flow rate changes very little over the operating pressures.
This slide is in reference to pump inlet suction guidelines. Getting the oil into the pump is the hard part. The positive displacement pumps will positively pump the oil to the destination. Best practice is to keep the pumps as close to the tank as possible. Try to avoid excessive suction lengths and inversions. Suction pipe sizing is critical when sizing. Quality positive displacement pumps will create 20 inches of vacuum. We like to design systems with a pump vacuum with less than 15 inches mercury. As a rule of thumb, pumps will work for buried tanks with a max lift of 20 feet from the tank bottom to the pump inlet. Although code calls for a pressure test on the piping, we also recommend a vacuum test on the suction side of the piping. Determining inlet suction. Determine gravity head in feet of oil. Figure the lift from the bottom of the tank to the pump inlet. Convert your fittings, your valves, your length of pipes. Add your losses through the strainer. And by the way, we like to size our strainers at a 1/2 inch mercury pressure drop through a clean basket. If your losses are too high, increase your diameter. And pay close attention to the suction line sizing, number of fittings, routing. Do not oversize, and what I mean is sometimes you get too conservative and you increase your pipe diameter, and if you have a very low pump flow rate and perhaps you have a buried tank, sometimes it's nearly impossible to pull a prime out of that tank if you have a 100-gallon-an-hour pump using a 4-inch suction line that has a dozen elbows and the tank is buried 3 feet below grade.
As John says, it really is critical to pay attention to the suction pipe sizing. Is it critical to the system operation? And typically I like to see the velocity in the pipe somewhere around 2 feet per second or less.
Types of pumps we use in the industry, they're all positive displacement type as required by code. The first is the internal gear pump. We typically recommend for smaller systems. Our range of use is 20 gallons an hour to 1,000 gallons an hour with discharge pressures up to 100 psi. Spur gear pumps we typically recommend for medium range systems, 200 gallons an hour to 30 GPM with pressures up to 300 psi. And then we have a rotary screw type pump we typically recommend for large central heating plants, data centers, hospitals, anything high end. That range of 20 GPM, 280 GPM, and up to 500 psi. Fuel oil systems applications. We have fuel oil boiler loops at high or low pressure. We have generator systems utilizing remote day tanks or belly tanks or headers. Most common duplex pump skids will have 100% redundancy. Other types of systems are triplex pump skids or jockey pumps, where there may be a farm tank of oil, tanks, and they like to move the oil around. There are return pumps, and there are filtration systems with oil pumps.
In New York City, it's one note is that you are not allowed to use return pumps on day tanks.
Right, and sometimes the riser piping goes up to the ceiling, and then it enters your generator room, and you have to drop down 10 or 12 feet to a belly tank, and that kind of poses a problem for the installation.
Boiler supply loop systems. Cast iron and fire tube boilers are typically supplied with burners with integral fuel oil pumps. These pumps by code are positive displacement pumps, similar to what we provide on our pump sets. They will always pump a constant volume. These pumps are always oversized, 1.5 times at a minimum of the consumption rate. A 5 gallon per hour burner might have a 45 gallon per hour pump. Care must be taken when sizing a transfer pump for multiple burners, as the pump rate is significantly higher than the burn rate. Low pressure boiler loop. Burners with integral pumps are piped in low pressure loop per NFPA 31, which only allows 3 psi on the inlet of the burner pumps. In this example, we are drawing fuel oil out of a tank and feeding 2 burners with integral pumps. The burners burn 100 gallons per hour, and the pumps are rated at 250 gallons per hour each. In the example, the transfer pump would be sized for the burn rate of the first burner and the pump rate of the second burner. So 100 plus 250 equals 350 gallons per hour, and applying a safety factor of 1.5 to 2 would equate to a transfer pump size for 525 to 700 gallons per hour. In a low pressure loop, use the pump rate of the last burner and the burn rate of all upstream burners. We like to always pump slightly uphill and put an inverted U at the end of the line to add a slight back pressure and to ensure the supply pipe is flooded with no air, as the storage tank acts as an air separator. High pressure boiler loops are used to feed large industrial boilers. These boilers are equipped with burners that do not have pumps. These burners typically require 100 to 200 psi supply pressure. Since there are no pumps, we are just concerned with the burn rate. Therefore, we size a transfer pump for the total plant burn rate times the safety factor of 1.5 to 2. We will use a back pressure regulating valve at the end of the line to set the pressure for the burners.
So Ed, I wonder if anybody's asking, how come there isn't a return line off of those burners back to the oil tank return line?
Well, since there's no pumps on there, we're not pumping more. We're not forcing more oil into the nozzle of the burner. So therefore, there's no oil to be returned to the main fuel oil supply pipe there. There are occasions though where they actually will put a scavenger pump on there when a burner is being pulled out of service. They can just pump the residual oil out of it.
Day tanks. Day tanks are used for emergency generators, boilers, and other fuel-burning devices. Used for remote limited supply at fuel-burning device and decouples the appliance pump from the main transfer pump on the bottom floor. We recommend a 2 to 4 hour storage at the remote device. Use drop tubes to prevent foaming problems. The return pipe can be extended at least half the distance to the bottom of the tank. For good circulation space, supply and return piping as far apart as possible, each near the bottom of the tank. And you must have a means to prevent overfilling. Day tank piping considerations. System design determined by either generator consumption or pump flow rate. Similar to boilers, there could be a large difference between the generator burn rate versus actual pumping rate. A good rule of thumb is each 100 kW of generator capacity will consume 7 gallons per hour. Generators that are piped with return line back to the day tank require a smaller flow rate as the transfer pump set is sized for consumption. Generators with return piped directly back to the main tank require larger transfer pumps. Try to avoid small day tanks on large generators as the recirculated return oil could overheat the small day tank. Note the flash point of diesel oil is approximately 138 degrees Fahrenheit, and generators typically have a shutdown sensor at between 140 and 150 degrees Fahrenheit. Remedies for keeping day tank supply fuel oil cool. Install a fuel oil cooling radiator to prevent overheating. Return directly to the main tank, bypassing the day tank. Or if possible, increase your day tank capacity. Then you determine your duty cycle of the pump set. Typically, on taller buildings, the rule of thumb is 4-to-1. And this could be buildings at 30 stories up. Sometimes with 3 or 4 or 10-story buildings, you may only use a duty factor of 3-to-1.
So, John, how long has that 7 gallons per 100 kW rule of thumb been used?
Since the cavemen.
That's pretty long. Didn't know they had generators back then. Maybe mid-1990s?
The 7-gallon rule per 100 kW has been around since I started in the mid-90s, so it's been around a lot longer than me.
And pretty accurate, right?
Very accurate. This is a representation of a typical New York City generator installation. The main oil tank is in the basement with the pump skid, and the day tank is located up at the generator on the upper level. This shows the generator return line piped back to the day tank. Therefore, the pump skid will be sized for consumption. The static head and piping losses will determine the discharge pressure of the pump skid. The overflow pipe per code must be 2 standard pipe sizes larger than the supply pipe. The maximum storage per floor above the lowest floor of a building in New York City is 330 gallons. And the roof is considered a floor of the building. The day tank must be vented locally to atmosphere, and you can install a T in the vent line and connect that line to the overflow line going back to the basement tank. We also recommend a switch in that vent line just in case the oil is going up that line. You'd like to know that's an issue. Be sure to keep supply and return lines as far apart as possible on tanks. For main tanks and day tanks, when the vent pipe is extended a long distance, you must be careful not to exceed the pressure rating on that oil tank. For flood zone buildings, refer to Appendix G of the New York City Building Code for your storage limitations. And UL 142 rated tanks are maximum 5 psi static pressure rated. However, the New York City alternate tank design is rated for 25 psi minimum. The New York City tank design allows the vent lines to be extended further and higher in elevation. This higher pressure rated tank must be used for installations with vent lines above 12 feet vertical or over 20 feet horizontal. Sub-basements and lower may require a higher pressure rated tank.
So, John, as you can see with the venting issue here, it's pretty difficult to use a UL 142 tank inside a building in New York City, isn't it?
It is very difficult. You have to meet your code requirements, and really the best application I feel for those types of tanks is outdoors or at grade someplace where you really are able to control the height of the vent line. This is a typical UL 142 belly tank and includes a working vent on the primary portion of the belly tank, 1 emergency vent on the primary, and 1 emergency vent on the basin side. All vent lines are combined and run to atmosphere. Note the overflow piped into the vent. Vent line is sized for vapor flow, overflow sized based on oil pump flow rate.
So, John, how do we decide that combined emergency vent in there?
Well, typically, we'll take the largest emergency vent fitting, which is typically on the rupture basin, and you're going to run that line out into your common. Your combined vent will be the largest fitting size, that diameter of that fitting, and that will be your common combined vent line. Day tank controls. Day tanks inside buildings can include an open-top rupture basin for containment. Day tank level control consists of a multi-point level switch, pump on, pump off, with high and low level set points. As you see in the cutout, our low point is approximately 40% day tank capacity. This allows the facility some time to respond to the low level alarm. Tank basin will include a leak detection switch. Pump supply and overflow connections shall include drop tube connections in the tank to prohibit foaming. FYI, the device with the red cap is the weighted emergency vent. These are illegal for use and installation in New York City.
If this inner tank here was a New York City built tank, we could just run one vent line off that main tank. Obviously, the rupture basin has an open top, so no need to vent that.
Yeah, and that vent line would be, depending on your day tank, is 2 to 3 inch diameter. Generators with a header system. Header is for use when day tanks are not practical. They are sized same as day tanks with a maximum allowable capacity of 330 gallons. This slide represents a double-wall day tank that is required for outdoor installations. Indoor installations can use a single-wall pipe with a containment basin. And your maximum supply pipe feeding this header is 4 inches in diameter. You will include leak detection, a foot valve for generator suction, and recommend a low-level sensor as a backup. As you can see, there is a vacuum breaker in the return line piped to a drum. This drum will include a breather and a leak sensor. We recommend the inlet supply pipe and the return pipe be at opposite ends of the header so you can get full flow through the header.
So, John, is there any code requirement around that low-level switch there?
Yes, there is, Ed. That switch is allowed to turn the pumps on only if the generator is in operation. So if the generator is off and they drained out the tank, the pumps will not start to fill that header.
Well, that makes sense. Long-term storage of fuel oil is very critical for generators. Diesel fuel is an organic compound which can decay over time. Many data centers and building owners want a large amount of oil on site in case of Armageddon. Most generator systems are tested per NFPA 110 guidelines. This creates an issue as very little oil is consumed throughout the year, and most generator manufacturers recommend a fuel oil maintenance system when the oil will not be turned over within 6 months to a year. The main issue with long-term storage of fuel oil is because tanks are vented to atmosphere, which allows condensation/water into the tank. When this happens, the water ends up at the bottom of the tank. This creates a barrier level between the water and the oil, in which bacteria thrive and create a layer of sludge on the bottom of the tank. Where is the pump suction drop tube? At the bottom of the tank to get all the oil out. So this means that sludge is going to your generator. It's not good. Generators have a 10 micron filter that will clog and shut the generator down in the middle of the blackout. The solution is a fuel oil maintenance system. These both dewater the fuel and oil and filter down to 5 microns. We recommend a dedicated supply and return pipe on the opposite ends of the tank to ensure fuel oil turnover. We also recommend dedicated supply line to ensure the filtration system drop tube extends lower than the transfer pump supply drop tube.
So Ed, with this bacteria interfacing with the water and the oil, how does that affect a steel tank?
Well, steel tanks don't like that water down the bottom of them, that sludge. So yeah, there has been some premature failure of steel tanks, especially with those ultra-low sulfur and biofuels. This is a typical fuel oil maintenance system. These are standard designs capable of filtering up to 2 20,000-gallon tanks. A typical system will filter the sludge from oil down to 5 microns, remove water from the fuel, and a self-contained leak detection and alarm. Large custom skidded filtration systems used in systems of multiple tanks includes filtration to 5 microns, water removal, chemical treatment, automatic PLC controls for sequencing multiple tanks.
And so, Ed, looking at this large filtration unit here, you have a horizontal tank, and you got this vertical tank with a hand pump, and then to the right of that, another cylindrical tank.
Well, the cylindrical tank is where your filter cartridges are, with the high pressure lid with the ASME lid on it there. The tank closest to us is a biocide tank, the horizontal tank, for injecting a biocide to help stabilize your fuel or lengthen its usability. And the big tank in the middle there, that's your water holding tank, your wastewater holding tank. And that's where you pump the water out there and you hopefully get rid of it per DEP guidelines.
Hopefully you don't fill that tank up too much.
Now, if you fill the tank up too often, you may want to think about a new fuel oil supplier.
Nice.
We have available a fuel oil systems program used for system design. This example is a typical New York City generator installation with a main fuel oil tank pump set located in the basement and the day tank located on the 10th floor. In this example, the pump suction is 14.25 inches mercury, which per our previous slide is less than 15 inches. Therefore, this system will operate without any issues. This is the output of our program that shows the primary pipe size, the piping friction losses, the fitting losses, valve losses, fluid velocity, and most important, the NPSH-A and NPSH-R. Example of a control system for our fuel system showing pump set control, tank gauging, leak detection, and overfill alarm. Fuel oil system controls can be as simple as a handoff automatic switch or as complex as a PLC-based system. The main advantage to the PLC is that they can talk to your building management system or a cloud-based system.
So Ed, the BMS is great, but I think I see a trend towards internet cloud monitoring.
Well, sure, it's a great way to let your people know that there's a problem in a building versus having a call from a tenant.
So they get a call from the cloud instead of the tenant?
Correct. These are typical shutdown conditions we recommend. Leak in the riser, leak in containment piping, leak in the day tank, leak in the pump set, loss of flow in the pump to protect the pump, day tank high level, and oil in the vent line. The leak in the riser, leak in the day tank, and day tank high level are code required shutdowns in New York City.
New York City fuel oil code caveats. For day tanks above the lowest floor, you must have 200% containment. Your maximum is 330 gallons of storage per floor. UL 142 tanks requires both the operating and emergency vent lines terminated outdoors. New York City alternate tank design, 25 psi G rated tank, requires its operating vent be terminated outdoors. Also, the New York City alternate tank design tank does not require an emergency vent. 1 day tank per pump set. Tanks in the basement over 660 gallons requires a means of spill containment at the fill box. All basement tanks are in a 2-hour fire rated room minimum. Riser pipe requires leak detection with pump shutdown logic. Anti-siphon valves are used on tanks when the inventory is above the pump inlet. A foot valve is required when the tank inventory is below the pump inlet. You'll have a leak in the riser piping monitored with a drum. Fire valves are provided on the pump suction line and the inlet to the generator room and all fuel burning devices. Some parting rules of thumb. Thank you all for listening. Ed, great job.
You too, John, also. If you have any questions, we will now go live for your question and answer session. And if you have any detailed questions, please also feel free to email us directly.